I trust you're fine wherever you are. This is the BSc in Economics 1.2 class, and to take you through Mathematics for Economists 2, my name is Moya Kihumba. In today's lesson, we'll be looking at linear programming. What is linear programming? Linear programming is a branch of mathematics that uses linear equalities and inequalities to solve decision-making problems that involve maximization and minimization problems. Maximization problem would be perhaps we want to maximize our utility. It could be perhaps we want to maximize our profits. Whereas minimization problems would involve minimization of costs. We also define linear programming as a mathematical criteria for minimizing or maximizing a linear function of several variables subject to a finite number of linear restrictions. In other words, with linear programming, we have an objective of either maximizing or minimizing a goal with several sets of variables and also with a given number of restrictions. Linear programming, therefore, sorry for that. Sorry, let's continue with that. Linear programming, therefore, is a branch of mathematical programming technique that involves the optimization of a linear function known as objective function, subject to a set of linear equalities or inequalities known as constraints. So we are saying that this is a mathematical technique in which we try to optimize a certain variable, which we'll be referring to it as objective function. If we want to maximize our utility, the objective function is utility maximization. If we want to minimize our costs, the objective function is cost minimization. Of course, subject to given constraints. Probably we want to maximize our utility subject to our income, or we want to minimize our cost subject to various expenses that we may incur. In other words, then, linear programming is a technique which helps us find the optimum solution for a given problem. It is a technique that helps us determine the optimum solution for a given problem. But what is an optimum solution? An optimum solution would be that which should give us the best possible outcome for a given problem. So our goal is always to meet our objective, but doing so in a way that we get the best possible solution. Linear programming has got two components which are linear. The first one is the objective function, and this is the primary goal of the formulation. Like we mentioned, we want to maximize our utility, we want to maximize our profit, or we want to minimize our cost. That is the first component, the objective function. And then the second component is the constraint. What are those conditions under which the optimization must be accomplished? If, for instance, we want to to maximize our utility. We'll maximize our utility subject to our income. All right. We will maximize our output subject to materials available. We shall be able to get highest grades subject to the hours that we put in our revision. So that is the constraint set, the our income, the machine hours available, the the man hours that we put in our revision, and so forth. Now, what are the basic requirements for a linear program? For us to apply linear programming technique, we'd have to meet the following requirements. The first one, we must have a goal or an objective which we can clearly identify and measure. And we identify it and we measure it, but the measurement must be in quantitative terms. Even that utility that you're talking about, we know we can measure utility using units called utils. The second requirement is that the activities to be included should be distinctly definable and measurable in quantitative terms. How much time, how many hours are you putting in your revision? How many hours are you spending in your mathematics for economists 2? And so forth there. Then 3, the resources of the system which are allocated to the attainment of the goal should be identifiable and measurable quantitatively. In other words, they are scarce, they are limited in supply. Not everything we are saying it is identifiable and should be measurable. There should be various alternatives in which we can be able to identify the scarcity of the resources that we've got. Now, we have got certain assumptions when we are dealing with linear programming. The first one is that our variables, the objective and the constraints, must be known with certainty and should remain constant over a duration of time. We also assume that they must be linearly related, all of them. If they are not linearly related, then we may not be able to solve the linear programming problem, and it must relate to a period of time. It is a one period. It is a one period solution. That's what we mean by static time period. The other assumption is that there should be proportionality. If you spend 10 minutes and you earn 2 marks, then it means if you spend 20 minutes, you should have 20 times 2 marks. All right? In other words, there are neither economies nor diseconomies of scale. We neither have advantages of large scale production or disadvantage of the same, and we have got no learning curve. All right? And again, this must hold if the linearity equality has to hold. Okay? Then it should be additive. We are saying in an LP system, the sum of individual activities for the two systems should equal to the sum of individual or separate parts. That is to say, if we have a table costing 200 shillings and a share costing 300 shillings, then we should be able to compute the cost of 500 shares or 500 tables and 450 shares. We should be able to compute that. Then there's divisibility. Divisibility assumes that we can divide into smaller parts. So long as our solution takes any value between 0 and above, nothing below 0. We'll see what is nothing below 0 would mean. Therefore, we could have 0.56. That's what we are assuming. we could have 10.5 seats. In other words, we assume that the decision variables are continuous and they are discrete. All right. Then there's a non-negativity constraint. If you sit for an examination, you're not going to get negative marks. If you carry out production, you're not going to get negative output. It is either zero or a positive output. So that's what means we cannot have variables which are negative. Actually, even our constraints can also not be negative. They have to be either zero or a figure above zero. Now, there are certain advantages of using linear programming to derive optimum solutions. And the first one is the attainment of optimum use of productive factors. We are able to use our factors of production optimally. It helps us make quality decisions. It would improve knowledge and skill of tomorrow's executives. That's you, students. In future, you expect to be making decisions. It will highlight bottlenecks in the production process. Now, bottlenecks are those challenges. They are those things that slow us down. And when you use linear programming, we are able to identify them. We've got others. We are able to get insights and perspective of the problems that we are saving. Then next, we can consider all possible solutions to the problems. And finally, it is a better tool for adjusting to meet changing conditions. However, linear programming has got certain limitations or certain disadvantages. And the major one is the treatment of all relationships as linear. And really, they are not really linear. You can't say, since you spent 100 hours in this unit, you should also get 100 marks. There should be some relation into that. You spend some of these relationships are not really linearly related. Someone may spend 2 hours and score an A, and another one may spend 10 hours and score an E. All right. So these really not all relationships are linear. All right. The assumption that we can divide activities is also a limitation because, for instance, we cannot have a share. All right. Now, unfortunately for linear programming, we can only look at one objective or one goal at a time. Either we look at profit maximization or cost minimization, but not both. Although it's a coincidence that in real life, actually, you can't do profit maximization and cost minimization at the same time. It's not possible. Though that happens in real life, even when you come to linear programming, you cannot take multiple objectives. You can only take one objective. For instance, you cannot say you want to maximize max. When you're trying to solve a problem for maximization or utility maximization, you look at perhaps this unit and a different one. You'd have to compute them differently. Again, this assumes certainty that everything is known, whereas we know in reality, not everything is known with certainty. Despite the limitations, we have several areas that we could apply linear programming. The optimal solution that we get, we can use them in perhaps to portfolio selection problem. These are on investment decision. How do you make your investment decision? Transportation problems. What would be transportation problem? Which planes do you send to what part of the world? Product mix. In order to get the optimum production mix, you can use it in campaign strategies, or you can use it to determine the amount of fertilizer to apply per acre. Now, not all in linear programming is theory because most of our time we'll spend it on computation. And the first thing that you do, the steps that you follow, is that number one, you have to define the problem. What you define as the problem is what is it that you want to achieve? What is the goal? What is your objective? All right. Then, are we dealing with resource allocation? And if that is the case, then you are better suited to use a linear programming problem, which is better suited for maximization or minimization variables. Then you'd have to define the decision variables. What are your constraints? Okay, and number 5 and number 7 are related. So is number 1 and number 4, because when you say define the problem, you're actually determining the objective function. Thereafter, you'll have to collect the relevant data, and most of those things will have been given for you, and thereafter, you'll have to formulate and solve the problem. So what we are saying then, you must understand the given problem, and thereafter you convert it to a linear programming problem, which we said there are two aspects which are involved in the formulation and solving of a linear programming problem. The first one is the formulation part, and the other one is the solution part. In this video, we'll deal with the formulation part. In a later video, we'll look at the solution. Please take some time and you look at that question. Maybe you may want to copy it down. We are told a firm manufactures and sells two types of products, M and N. The cost of production of each unit of M and N is shillings 2,000, and 1,500 respectively. A unit of M earns a profit of shillings 500, while N earns a profit of shillings 150 after they are sold. The firm estimates that the combined monthly demand of the two products to be maximum of 5,000 units. The firm has set the monthly production budget at shillings 500,000. How many units should the firm manufacture in order to earn maximum profit from the monthly sales of the two products? Now, clearly, this is a maximization problem. We want to earn maximum profit from selling several units, but there are constraints. What are the constraints? One of them is that we can only sell combined units of 5,000. You can only sell combined units of M and M, maximum 500,000, and our production budget is 500 shillings. We could put this information in tabular form for us to understand it better. You notice on our products, we've got product M and N. We've got cost of production per unit, which is 2,000 for M and shillings 1,500 for N. We've got profit per unit, 2,000 and 150 for M and N respectively. And the total demand for the two items is 5,000 units. Thereafter, we've been given our production budget as shillings 500,000. Now, how do we formulate this problem? The first thing, we are going to assume the units of M to be produced to be X, whereas those units of N to be produced to be Y. The total cost then would be 2,000X plus 1,500. Why 2,000X? Because we spent 2,000 shillings to produce a unit of M, which we are referring to X, and 1,500 to produce a unit of N, which we are referring to as Y. However, our budget cannot exceed 500, and therefore we could write the budget constraint, which of course is a constraint, as 2000x plus 1500y should not should not exceed 500,000, should either be less or equal to 500,000. That's our budget constraint. But we've also got our total demand constraint, which we said cannot exceed 5,000. The combined number of units of X and Y that can be demanded can at most be 5,000. So our demand constraint then will be X plus Y, should be equal to or less than 5,000 units. Now, if we let our total profit to be Z, then Z is equal to 200x plus 150y is our objective function. Why 200x? 200 is because is the profit that we earn from selling a single unit of M. At the unit of M, the number of units of M to sell is X, whereas 150 is the total number, is the profit that would make by selling units of N, which we are referring to as Y. Therefore, we could write our problem as maximize Z, which is equal to 200x plus 150y, subject to, these are the constraints. The first is the budget constraint. 2000x plus 1500y should be equal to or greater than 500,000 shillings. We have other constraints. X and Y should be less or equal to 500,000. That's our demand constraint. And those are the constraints that you have seen so far. But there's another one that we mentioned. There's an assumption we said non-negativity. We cannot have negative constraints. The number of units of M we produce, the number of units of N we produce must either be 0 or greater than 0, but they cannot be negative. And therefore, we introduce our non-negativity constraint. Since the number of units cannot be negative, we must add the non-negative constraint. And mathematically, we can write it as follows. X should be greater or equal to 0. In other words, we can produce either 0 units of M or more, and then Y should also be greater or equal to 0. So that is the formulation part. Okay, that is the formulation part. That then will mark the end of this video, but we shall mention again how we highlight our problem. We show our objective, which is to maximize profit, which is Z, subject to the budget constraint, the demand constraint, and the non-negativity constraint. Thank you. You could also subscribe to this video so that you can get many more. Asanteni.